Good day. From the previous video that we have posted, my colleague has derived a transfer function model for a continuous blending system. Well, now that we have a transfer function model, how can we solve the process if we are given the value for k1 and tau? In this example, we have a step change which is u prime. So with a step change, the equation, the transfer model will have an extra 1 over s. So it is very easy if we plot this, if we have a suitable code to solve this with Matlab. So now let's proceed to Matlab and let's see what we can do. So firstly, we'll always start off with a CLC comma clear, because this is to clear all the relevant data in the worksheet that might interfere, might create conflict with our data later. So firstly, we have to define t. While t is equal to, in this example, we define t is in the range from 0 to 1. However, we have to define how the step size, the step change for t, which is 0.01 in this situation. And after that, we can measure the length of t by using this code. So from the example that I've shown, firstly, if we are able to use hand calculation to develop the inverse the Laplace, and we have able to get a expression like this, it would be easier, but it's a bit tedious because we have to use hand calculation. But since we have the expression already, we can solve it with using Matlab as well. So now I command this as hand calculation method. I create a loop. This is a for loop whereby it will do iteration from 1 to max. Max is the length of t, which is the how many number of variables in t that we have defined. Don't worry, Matlab will do all the tedious job. So after that, we define y call as the expression that we have mentioned just now. Well, this is the equation. So when you put it into Matlab, it will be slightly different, but it's the same. It's 10 multiplied by 1 minus exponential of negative 10 times t, whereby you have to define t with I, because t is an array, and with the for loop over here, it will calculate the t 1 by 1, and then we have to put an end to this for loop. Also remember to put this small semicolon over here, so that it won't present all your data on your worksheet and create a messy worksheet. So however, if we do not have a expression developed from the hand calculation, we can also use the built-in function in Matlab to do the to calculate the transfer function. So first, we have to define the numerator. In this context, it's 10, which is the k1. After that, we define the denominator, which is 2, which is a tau, and also 1, which is the constant. Well, in this case, it's not 2, it's 0.1. So after defining the numerator and the denominator, this is a Matlab built-in function, whereby it's a TF, transfer function of numerator and denominator. Also remember that there's a step change in this example, so we have to use the Matlab built-in function to analyze the step change. And remember, this is SYS, this is what we have defined earlier, and also with t, with respect to t. So after we have developed our codes for hand calculation and also transfer function method, we need to compare the results of this and see whether they match each other. So the best way is to plot a graph. Well, we first label the graph as figure 1, plot the graph. While O is actually orange, it will give the color to the graph. And again, this is T, Y same, and I'll color it as red. Remember to label your legend, which is the first one should be the hand calculation, and the second one should be the simulator. So after that, label the graph. The X label should be time T, while the Y label, it's Y to the power of prime with respect to T. So that's our code, and let's see, we'll click F5 to run it, save file and run. We'll save it as modeling 2. And there you go, we have a graph plotted comparing the hand calculation and the simulated. Well, from here you can see that it's the same, and both methods can be used to solve a derived transfer function model. Thank you, and we hope to see you again.